now that we've talked about the basic definition for a function, we're going to want to categorize them a little bit further by having some more precise definitions. And so if we have some function f from a to b, then we can talk about f being one-to-one, onto, or bijective. And so each of these will talk about different properties of the function. And so one-to-one is often called injective. And we say that a function is one-to-one or injective if whenever the outputs match for the function, then the inputs had to match as well. And so often this is easier thought of as the contrapositive of this statement. And so I could write the contrapositive just in this corner right over here. So if a1 is not equal to a2, then that implies that f of a1 is not equal to f of a2. That would be the contrapositive. Another way of saying this more intuitively is that a function is injective as long as all of the inputs go to different outputs. Then on the other hand, we can talk about a function being onto or surjective. Those mean the same thing, they're just used interchangeably. And that would be if everything in the codomain is hit by something. And so more formally, we could say for everything in the codomain, there is another thing in the domain such that f of the thing in the domain is equal to the thing in the codomain. So that's a lot of words, but it just means that we can find an input that hits our desired output. And then one-to-one correspondence or bijective is not too bad. Once we have these, it just means both things at the same time. And so let's look at a particular function, f of x is equal to 2x, and show that this is a bijection. And so this is a function mapping R to R, and it is important that we specify the domain and the codomain here, because sometimes if you have the same function on a different domain and codomain, then it could change whether or not it's a bijection. And so first of all, it'll be helpful just to draw this function's graph, just so that we can make sure that we understand what's happening here. And so if I draw this function, which is just the line with slope 2, then surjective in particular just means that everything on the y-axis has a corresponding value where it's hit. And so in other words, for every y value here, I could go over and I can find somewhere on the function where it hits. Injective means that a function or a value is never hit more than once. And so that would just mean that every time I draw a horizontal line here, it only intersects the function at most once. And so we really could view this then as injective says each horizontal line hits it at most once, and surjective says that it hits it at least once. And then bijective would mean that it hits everything exactly once. Often we won't be viewing functions as from the reals to the reals, and so we won't be able to have the same graphical interpretation, but it still might be helpful to think about things this way some of the time. Okay, so now we're ready to prove this using the more formal definitions. And so the first thing I'll want to show is injectivity. And so following this, I'm going to show that f is injective. And so what I need to do is take any x and y in the reals where f of x is equal to f of y. Right, and so I'm starting by assuming that we have some inputs where the outputs match. And then my end goal should be to show that the inputs had to match as well. And in between here, I just need to use the definition of the function. But always this sort of outline here between take any inputs where the outputs match and then show that the inputs are equal, that's the structure for an injective proof. And so you should always be able to write the first and last line of an injective proof regardless of what function you're talking about, because it always looks the same. Okay, and so now we just have to connect the dots by using the definition of this particular function. And so if f of x is equal to f of y, I can plug in, and that just tells me that 2x is equal to 2y. And then if I just divide by 2, then of course I get x is equal to y. And so in this case, the proof for injectivity was pretty trivial, but the point of this was to just see that proof structure. Okay, now we can show that f is surjective. And so in this case, then we're going to want to find or take anything in the codomain and then find something in the domain that hits it. And so we'll let y, we'll say, be inside the codomain. And this is really similar, really, to showing that the range of this function is equal to the codomain. And so in order to do that, again, like the previous problem that we talked about, we might want to do an aside here. And so we want to find x such that f of x is equal to y. And then I can plug in what f of x would be. And then I can solve for x in terms of y. And so in this case, I know that the appropriate input would be y over 2. This function, again, is really simple, and so you probably could have seen that without writing this out, but some of the time when the function's more complicated, you'll have no choice but to do some sort of aside here to solve for it. Right? And so in this case, then I can say that y over 2 is in R as well, and f of y over 2 is equal to 2 times y over 2, which is equal to y. And so that implies that y is hit by f. And since y was arbitrary, that implies that f is surjective. Now that we have that, all we needed to show overall was that this is bijective. And since it's injective, and also surjective, that just by definition means that f is bijective.